Hi, I'm Professor Rodney Van Meter from Keio University's Shonan Fujisawa campus and the Faculty of Environment and Information Studies. Welcome to Linear Algebra. Welcome to my classroom. You're probably taking this class in order to get some credits at Keio, probably your Data Science 1 credit. But before we dive into all the mechanics of what you have to do in this class in order to earn those credits towards your graduation, I want to spend about 20 minutes talking about why we ought to be studying linear algebra. I want to get you excited about this topic. First off, this is a picture of a black hole. I hope you all saw this last year. This picture was released on April 10th, 2019, which happens to be my birthday, so I thought it was a tremendous birthday present for me because I'm a big astronomy fan. This you're seeing here is the first picture ever taken of an individual black hole. It sits at the center of the M87 galaxy, which is 55 million light years away. In this picture, what you're seeing is a space about 1,500 light years across. So about the distance that it would take light 1,500 years to cross. And the size of the black hole is about 1 light hour across. Now there are 8,760 hours in a year, so that's on the order of 13 million times the size of the black hole in this picture. So the black hole itself is about 1/13 millionth of this picture. Now, obviously that picture wasn't taken with an ordinary optical telescope. It was taken with a network of other telescopes that collectively make up what's called the Event Horizon Telescope. This is an image of an animated movie that the Event Horizon team put together. You can find that on YouTube. I highly recommend it. And in that video, they describe some of the data processing that was actually conducted to do this, which, well, what a surprise, requires linear algebra. The overall technique that they're using to create this image is what's called Chocho Kisen Dempa Chos Kanshoho. Sorry, let me say that again. Chocho Kisen Dempa Kanshoho. There we go. Very long baseline interferometry. Very long baseline interferometry is the technique where they match the timing of those signals and bring them all together to form one complete signal. The Event Horizon team has published a series of papers describing this. They are available on the web. You can look them up. This was such a big deal that they held a large press conference to announce the result. The woman in the fuchsia-colored jacket there is France Cordova. She was the director of the U.S. National Science Foundation at the time, and she's a Caltech graduate. I'm a Caltech graduate, so of course I was very proud of her role in doing this. At the top, you'll see an image, an outline of the processing that they had to do in order to build this final image. And they started from 5 petabytes of raw data that was ultimately processed to give you that one little image that we saw a couple of minutes ago. A lot of that processing is, in fact, linear algebra. Okay, so that's beautiful, and it's one of humanity's most incredible accomplishments, but, I'm not an astronomer, so why should I take linear algebra? Why should I study linear algebra? Well, did you all see the movie Hidden Figures? Raise your hand if you saw the movie Hidden Figures. I saw the movie 3 times in the theater, and I cried every time. It's one of my favorite movies. I loved it. It's the story of a group of women, mostly African-American women, who are computers during the early days of the U.S. space program. One of the central characters in it is a mathematician named Katherine Johnson. Here's a picture of actress Taraji P. Henson playing her in one of the scenes. The mathematics she's writing there on the board is probably a little bit more complicated than linear algebra, but same general area. Now it happens that Katherine Johnson is from West Virginia, and I'm from West Virginia, so I'm proud of her being from my home state. She's a graduate from West Virginia State. It's now a university. At the time, it was West Virginia State College. And my brother-in-law is a graduate of West Virginia State, so my sister and he went to a ceremony where they dedicated a statue of Katherine Johnson on the West Virginia State campus, which was the African American, historically black college in the state of West Virginia at the time. Now that picture in the middle is from Wikipedia, and it's an image of Katherine when her job was actually computer. At that time, a computer was not a machine. A computer was a human who did calculations. And of course, a lot of what she did was linear algebra. Okay, so putting John Glenn into space was another one of humanity's greatest accomplishments, but I'm not sending anybody into orbit, so do I need to study linear algebra? Personally, one of the things that I found most fascinating when I was in graduate school, and that completely changed the way I think about a lot of computing systems, is an area called queuing theory. Now this applies not just to computer systems, it applies to banks and grocery stores and any place else where you can stand in line and wait for your turn for something. That's what queuing theory is. It's the study of how long you have to wait, the statistics of such processes, what happens to systems like that as they evolve over time. So the internet, computer processing, banks, grocery stores in particular kind of matter in this day of COVID. How long are you going to have to wait in the grocery store? Again, linear algebra forms some of the core mathematics you have to perform in order to solve problems in the field of queuing theory. Okay, but I'm not designing computer servers or networks or banks or even grocery stores. So, do I need to study linear algebra? Well, do you care about the security of your data on the internet? You're sharing credit cards and private emails and whatnot. Then you're using cryptography. Cryptography is where you take a message and you apply a mathematical transformation to it so that it's secret and nobody can read it except the person it's intended for. That's what you call cryptography. This is a device that was designed actually by US President Thomas Jefferson for encrypting a message. It was actually used by, one similar to this was used by Lewis and Clark on their expedition. I 3D printed that using my own 3D printer, which we'll talk about here in a minute. Okay, cryptography. Yeah, I mean, security is important and all, but, right, okay. There's also the matter of the images you're seeing on the internet are not always the full resolution images. Often they're compressed in order to actually reduce the amount of data and bandwidth that you need in the network. On the screen here, you're seeing 3 examples of how what's called lossy compression gets applied. So compression comes in 2 flavors. There's lossless and lossy. Lossy compression reduces the amount a good deal more, but it results in problems with the image like you're seeing here on the screen. This is a famous image. The URL where I picked it up on the screen is listed there, but it actually goes back quite a bit further than that. All right, so image compression is a worthwhile use of mathematics, but I'll let somebody else deal with that. All right. Maybe I'm interested in economics. Maybe you want to be in Professor Wada's group here at SFC. He studies the economy, and that requires a certain amount of mathematics. One of the most important types of mathematics that you need in order to work in economics is statistics. You probably have learned a little bit of statistics already, but in fact, more advanced statistics depends on not just probability, but also on linear algebra. So you combine the two, you put them together. Okay, but I'm not an economist. All right, well, maybe you're interested in biology. Great. SFC is the home to KO's Institute for Advanced Biosciences, and one of the things that they do very well there is what's called bioinformatics. Excuse me. Bioinformatics is the study of the information in living things. The information in DNA, the information in proteins, how that data gets transferred from one place to another and how it gets used, studying the behavior of that information at sort of a statistical level, those sorts of things. It's considered so important that, as you can see here, Harvard put together an online course for this, an introduction to linear models and matrix algebra, specifically for people in their biosciences programs. Yeah. So biostatistics and bioinformatics for genome stuff is pretty important, and applying statistics to world health maybe makes the world a better place. Yeah, hey, that's a good point. Maybe you're interested in working with Professor Akiyama or Professor Kunieta. Both of them would be really thrilled if you showed up at their Kinkyukai or their classes with a solid understanding of linear algebra and statistics, because it affects the way global health gets managed and communicated to people. Okay, so that makes the world a better place. But, all right, maybe you're interested in computers, or maybe you're interested in business. Those are two things that people here at SFC are commonly interested in. Both are influenced by a field of mathematics called optimization theory. I used to teach this class. Now it's taught by Professor Kawashima here at SFC. You should take it, and it would count as your Data Science 2 class as well. So it's a good class to take. So what is optimization theory? This is a map that my friend Scott made of a motorcycle trip he took a couple of years ago. He started from his hometown in New Jersey and drove through the state of West Virginia. The state of West Virginia consists of 55 counties. Each county has a county seat, and in each county seat there is a county courthouse. His goal was to travel the state of West Virginia and take a picture of his motorcycle in front of every single one of the West Virginia state courthouses. Great. So how do you do that so that you follow an efficient path rather than going back and forth, north, south, east, west? How can you form a pretty efficient path through the entire state? That's an optimization problem. Maybe you're interested in running a factory. This photo is a couple of the machines at Keio's Yagami campus, where they have a center for studying manufacturing. One of them is a 3D milling machine that can cut away metal to leave a particular shape. The other one uses metal in a 3D printing process. So these gadgets, the gadget that I just showed you was printed out of plastic, but it's also possible to print out of metal. So optimizing the use of materials, but also not just, so the optimization problem inside one of these machines, but also the optimization of the entire factory itself. How do you minimize the amount of material you need? How do you organize the flow of your system? How can you maximize the throughput of your factory? How can you maximize the amount of money that you're going to make out of it? Hey, that's an interesting problem. How do you maximize the profit for a business? Well, you can set up a set of equations that represents your business. How much it costs you to build a particular thing, how much your rent is, how much you have to pay for the individual machines, how much you have to pay the workers, and your costs for sales and whatnot. And you can put it all into a mathematical model and solve it. That's an optimization problem. And that way you'll maximize the amount of money you make. One of the tools you might use for doing that is an algorithm called the Simplex Algorithm. Now, a simplex happens to be a triangle. Now, this is a triangle in 4 dimensions. Well, actually, it's the 3-dimensional map of a 4-dimensional triangle, but you get the idea. So a simplex is an n-dimensional triangle. As you can see from the figures here, that the simplex algorithm applies not just to those triangles, but also to shapes of different sizes. It's a method for finding an optimal result in a set of linear equations. We'll talk about that a lot during the course of the semester. There's also a class of problems known as graph problems. Graph problems can be represented, as you see here on the in this picture taken from the page of the textbook that I showed you a minute ago. In a graph, you have the circles with the letters in them. Those are what are called nodes or vertexes. And the edges, the lines connecting them, are what we call either a link or an edge, depending on sort of the terminology you're using. Our question is, what's the least expensive path that carries us from node A to node E? Maybe the weights along that are the number of hours you might have to drive if this is a problem where you're talking about driving from one place to another, for example. I actually took that problem and I created a 3D printed model of that as well, actually, when I was teaching the class a couple of years ago. But those are what you call linear problems. But there are also nonlinear optimization problems you can see in this. This function includes what are called nonlinear terms. We'll talk about what that means. In this case, maybe we're looking for the lowest point on this surface, and it happens to be here. How do you find that point given a mathematical representation of the particular surface? All right, so optimization theory sounds useful, and I get it. It's useful for business, and I get optimization theory requires linear algebra, but it's still really kind of not my gig. Did you see this a couple of years ago? Any of you play Go? I play Go. If you play Go, let me know. Maybe we'll find a chance to play sometime. A startup company created a program. The company was bought by Google, and their program is called AlphaGo. It played against a player named Lee Sedol a couple of years ago. And Lee Sedol is one of the very best players in the entire world, one of the best players in history. AlphaGo beat him. So this is considered a milestone in artificial intelligence or in machine learning or in deep learning. Now, deep learning is one of the terms that we use for describing a particular type of, it's a subfield of machine learning, which is a subfield of artificial intelligence. It's one of the most popular forms right now. Deep learning builds on mathematics. There was a big transformation in the year 2012. This textbook was written in 2016 and describes it. So I highly recommend you get this textbook. I believe it's available online for free as PDF. Okay, so machine learning is amazing, and a lot of people at SFC are working on it, but it's still not really my my kind of gig. So what's next? Well, how about this? How about this? I have a 3D printer in my office. There's the parts. When it was done, it looked like this. You recognize this? This is the USS Enterprise from the original Star Trek series from the 1960s, debuted in 1966, the year I was born. I printed this on my printer here. I did not design it. The design I found on the web. But it did not fit on my printer when I got the design files. It was designed for a larger printer. So I had to shrink it down and scale it down. How did I do that? Linear algebra. Okay, I got it. So linear algebra has lots and lots of uses. One final one. My research group, my Kenkyukai, we are working on quantum computing and quantum networking. We are working to design the quantum internet is one of the various tasks we're doing. Here's an image of the quantum internet simulator that we've created. If you're interested in this, you should come join us because this is an opportunity to be involved right at the leading edge of technology anywhere in the world. And as undergraduates, you can contribute to this. All right, so that's amazing. The quantum internet's being designed and hopefully built at SFC. I want to be involved. Okay, great. Come join my Kenkyukai. So, finally, linear algebra is a branch of mathematics, but the truth is that linear algebra is the mathematics of data. Matrices and vectors are the language of data. This was said by Jason Brownlee. The way I like to say it is, I view linear algebra as the power tool of mathematics. It's the thing that makes everything else more powerful and ultimately more possible in the hard work of actual computation. So, I hope you've gotten some idea of why we want to study linear algebra. We'll talk in the later video segments about the specific topics, the mechanics of running the class, what will be expected of homework, what the technical topics are that you'll have to learn. We'll cover all that later on. If you're curious how linear algebra fits into the overall world of mathematics, I highly recommend this video, The Map of Mathematics, which was posted by a YouTuber who goes by the handle of Domain of Science. And you'll see how linear algebra fits into a large number of fields of mathematics. It's there just to the upper left of that circle in the middle It's one of many different things. It's a fascinating one. So come join me. I'm looking forward to having you all in class, and let's get started.